and controlling its transport properties. Over many years of intuition, research and development, literally from ancient times to now, we became experts in engineering the real part of the index by spatially and even temporally varying it. In fact, index crafting has now reached a level of maturity that we can make lenses for microscopes and telescopes, fiber optics for fibers for fiber optic communication, gratings for spectroscopy purposes, meta surfaces and meta materials for manipulating and controlling light transport and behaviors in nanoscale, and of course silicon photonics and all sorts of photonic integrated circuits. These are just a few examples. On the other hand, we have almost 50 years of conscious using of gain in optics, where it is used primarily to provide amplification, basically to compensate losses or boost signals. It has also, of course, enabled lasers and optical amplifiers that become very important and useful devices over the years. So almost 15 years ago, a new reality emerged, indicating that by judiciously designing both gain and loss, which is basically loss is just the other aspect of gain, and there are other variations, like for example, having a differential gain or a differential loss, one can find new ways to control to confine the light, control its propagation properties, and even govern its interaction with matter. Tasks that we previously thought that is only possible by changing the real part of the index. This now new field is now known as non-Hermitian optics. And so interestingly, light transport and confinement in these non-Hermitian systems is fundamentally different than what you expect from Hermitian arrangements. To start with, and I'm going to give a little bit of a background. To start with, let me actually introduce. Whenever we want to be able to compare these two systems, Hermitian and non-Hermitian, let me just first introduce what we know as a Hamiltonian of a system. In classical physics, Hamiltonian is usually the function that governs the dynamical response of the system. So let's say if we have a Hermitian Hamiltonian, the system now becomes Hermitian. And Hermitian Hamiltonians are basically, as we know from linear algebra, that means that this H or the function or the matrix that represents the system, let's say it's equal to its adjoint. It's basically self-adjoint. And that means that we have, for example, in this type of systems, you have all the eigenvalues real and all the eigenvectors orthogonal to each other. Now, if we have a two-level system, meaning that if you have a system with 2 degrees of freedom, this would be then represented by 2 orthogonal eigenvectors and 2 eigenvalues that, as I said, they are real. And of course, in this system, sometimes it happens that the 2 eigenvalues become equal to each other, and we know that particular point in the parameter space as a diabolic point or a Hermitian degeneracy. Now, as opposed to these Hermitian systems, we can also have non-Hermitian systems, which, again, just from linear algebra, we know that that basically means that their Hamiltonian is no longer self-adjoint. And such systems, again, from linear algebra, we know that they can, in principle, support complex eigenvalues, and they have eigenvectors that are no longer orthogonal to each other. So an example of this would be, for example, a 2-level system or a system with 2 degrees of freedom. In such arrangements, such non-Hermitian systems would be represented by 2 eigenvectors that are no longer orthogonal to each other, and 2 eigenvalues that, as I said, they are no longer necessarily real. So in such systems, in such non-Hermitian systems, also there's a possibility when we change the parameters in the parameter space, in this system we get to a point, a degeneracy point, where not only the eigenvalues become equal to each other, but also the eigenvectors become collinear. And we know these points in parameter space as exceptional points. So exceptional point is such a point in parameter space where the eigenvalues and the eigenvectors of a non-Hermitian coalesce on top of each other. Now, people, of course, were aware of the existence of such point, and this name exceptional point actually was given to these particular points by mathematicians, because they noticed that a system that is reaching this point will start to behave very differently from what you expect from standard Hermitian systems. Okay, so so what was actually missing and why we didn't use it before and why we started to use it more recently is because of the fact that we didn't know how to systematically generate these points in various physical systems. And this has changed actually from a very interesting and unexpected place, which is basically quantum mechanics. As we know, quantum mechanics, the standard quantum mechanics is actually a Hermitian theory. So meaning that all the physical observables, we know that they have eigenspectra, or what we know basically eigenvalues that are real. So back in 1998, Bender and Boecher asked themselves this very fundamental question: does it necessary for a system to be Hermitian in order to have real spectra? And interestingly, they found that the answer to this question is no. In fact, they were able to identify a family of functions or potentials that were not Hermitian, yet they had showed completely real spectra. And such family of potentials have this, or Hamiltonians have this property that the real part was an even function of a space, while the imaginary part was an odd function of a space. So not only they noticed that these functions are very interesting because they are not Hermitian, and yet they support real eigenspectrum and real eigenvalues. They also noticed that as they start to, they keep the system, and this type of potentials are actually known as PD-symmetric because they respect both the parity and time operations. They also noticed that when they start to change the parameters of the system and they keep them PD-symmetric, eventually at some point this the spectrum becomes complex, and that the spontaneous breaking of PD-symmetry, the point that this property happens, happened to be an exceptional point. So this is where the mathematics and physics met each other, and they started to form this new field of eventually non-Hermitian optics. The significance of this discovery, however, went unnoticed for almost a decade until my colleague from Creole, Dimitri Christodoulidis, and his students actually noticed, they basically used the isomorphism between Schrödinger equation and paraxial wave approximation, and they showed that this type of complex potentials that are not, at least not easily attainable in quantum mechanics, they can be very, very readily implemented in optics. So in optics, as we know, the real part, so first of all, the isomorphism between these two equations tells us that what you see here as the potential in optics is basically what the parameter or the function that plays this role is the refractive index profile. Now remember, refractive index has a real part and an imaginary part. And of course, for the real part of the refractive index, what is known, again, most of the time we refer to it as index. And then the imaginary part of the refractive index is what we know as gain or loss, right? So in optics, in order to get a PD-symmetric potential, we need to design a system where we have a refractive index profile that is even in a space, that its real part is even in a space, and its imaginary part is an odd function of a space. And this is, as you can see. Now, to give you an example as how this exceptional points emerges, let me give you this system. Let's assume that we have this optical system that we want to study is actually a coupled resonator system. Let's say each of these balls here is a resonator. There are two identical resonators. So the refractive index, the real part of the refractive index, is completely similar. There's a coupling between these two elements, which I draw it as kappa. If there are two resonators, you can imagine, for example, two microring resonators that are next to each other. And because of proximity, they are coupled to each other. So their field basically penetrates from one to the other one. So this coupling is simplifying that, indicating to this behavior. And then, as I said, they are identical, but then apply to one of them gain and the other one an equal amount of loss. So if you write the equation that is governing this basically system in the very first order, if everything is linear, you can write it as follows. So you can say that the electric field A of, for example, this element, and the electric field in the other element is B. And as I said, this is a coupled system. So, and one of them is subject to gain and the other one is subject to loss. Immediately in possibly 2 lines, when you write this matrix in the proper form, you can get the eigenvalues and eigenvectors of it. And you can see that at the point where G over 2 kappa becomes equal to 1, you can see that the 2 eigenvalues become equal to 0, and the 2 eigenvectors are becoming also exactly identical to each other. So it is basically with this very simple treatment, you can find the exceptional point in this system. So the parameter that you have is G over 2 kappa. That means that the changing of G over 2 kappa gives you the parameter space. By changing that, you can actually explore the system in the PT symmetric versus PT broken regime, which I will talk about them in a minute. So if we, as I said, if you look at this system, you can see that you have two, if you draw the real parts and the imaginary part of the eigenvalues of this system, you can see that the exceptional point sits over here in the middle, where, as I said, both the eigenvalues are equal to 0. That means that both the real part and imaginary part is equal to 0. Now, in the PT unbroken phase, as you can see, where G over 2 kappa or kappa, I mean, it doesn't matter, it depends on how you define this, it becomes less than 1, you can see that the eigenvalues are actually splitting in real part. And this is what most of you are familiar with it. So if you have 2 resonators next to each other that are coupled to each other, once they basically the coupling is established, the system behaves exactly like what you expect from a hydrogen atom, where you bring 2 hydrogen molecule, when you bring 2 hydrogen atoms next to each other, and there is a level repulsion, and you get the odd mode and the even mode to be actually separated in the frequency or in their resonances. So what you see here also is the same, or in the energy level. So you see the same thing. You basically see that the 2 eigenvalues become separated in the real domain. And then once you pass this exceptional point, you see that the system behaves extremely, completely differently. In fact, the 2 eigenvalues emerge to the same point in the real part, and then they start to separate and bifurcate in the imaginary part. So in that sense, above this point, you get 2 modes. Below this point, you get 2 modes that are equal in both resonators, and they are, the mode is basically looks like this. And basically, you can think about as one of them being 1, 1, and the other one is being 1, minus 1. I didn't draw it. This is the intensity, so you don't see really the phase. So both modes look like this. But while you pass the exceptional point and reach to the PT broken regime, what you see is that the mode reshape in such a way that there would be, for example, more of the, for one of the modes, more of the power will be in one resonator, and for the other one, would be in the other resonator. And that justifies why the 2 the imaginary components of eigenvalues, one of them positive, the other one negative, meaning that one of them is experiencing gain, amplification, and the other one experiences, attenuation and loss. And this is what you basically, that's the systems are representing. So you see very drastic and very abrupt phase transition in the system while it passes through this exceptional point. And this is basically was the motivation as well. The question that we basically ask ourselves is that how we can find this new design tool that basically how we can use this newly found design tool of non-Hermitian optics to benefit, whether it's for enabling new scientific discoveries or novel applications. So to address these questions, we looked at, there are many, of course, groups that looked at these behaviors over the years, and some of them are actually listed here. So what we did back in 2014, we looked at this and say, oh, this looks like this abrupt phase, the abrupt change and the abrupt phase transition that we observe is a very interesting and useful engineering tool. Can we actually use it for laser mode management? And these are number of papers that we published over years, and actually it's continuing. I didn't renew this slide. We have done a lot of work in this area, and these are some of the examples. So to give you an idea as how we can use this idea of this threshold that the PD symmetry breaking puts in the system as a way to control the modes of a laser, I will give you a little bit of a background. Let's say we just get a ring resonator. A single ring resonator can actually support several longitudinal modes over the. So if this is made of a material that can provide gain, like most semiconductors, not most semiconductors, 3-5 semiconductors, you can see that there is an associated gain spectrum or line shape to this gain material. So, and if these are the longitudinal modes of the cavity, no, actually, realistically, most semiconductors have 50, 100 nanometer, spectral length of gain. At the same time, let's say if we have a ring resonator with a radius of 10 micron or 20 micron, the spacing between these resonances will be about 5 nanometers. So immediately you can see that very quickly and very easily, these systems can become multi-moded. Of course, if you want to keep the system single-moded, that means that you have to really only you have to pump the system in such a way that only this mode that is happening to be at the highest point of the gain would be above threshold. But as soon as you increase the pump, immediately the system becomes multi-moded. Now, if by any chance you decide to pair this resonator with another resonator that is identical to it, you just doubled all your problems, in the sense that we know that because of this pairing or the coupling that you established between the two resonators, the modes are going to, each mode is split into 2, and that's what you get. So you basically increase the number of modes by a factor of 2, which makes sense. You made the cavities twice as much large. And you can follow it with this eigenfrequencies of this system will be given with this. And you can see that what we have here is the kappa, which is the coupling, and then gamma AQ minus gamma BQ. Gammas are basically the gain that you get from each of them. So if both of them are subject to gain, this an equal amount of gain, you expect this term to be equal to 0, and that's where you get the splitting of the resonances. So each longitudinal mode of the cavity, which I put Q for each of them, you can see that it splits to 2. Now, if on the other hand you put you put loss on this cavity, you can immediately see that from this same equation, you can see that now this term is basically, let's say we put an equal amount of loss, that becomes, this term becomes now equal to gamma squared. And now we have this equation that tells us what are the eigenfrequencies of the system. I see a chat message. Let me just see if there is anything that I have to answer. Nothing. All right. So so you can see that now at this point where the gain becomes exactly opposite amount of loss, so we get this equation. Now look at this equation. Looking at this equation, you can immediately see that for each resonance, it matters if your kappa is above the gain or below the gain. If it's above the gain, you're gonna get, if the kappa or the coupling is larger than gain, then you expect the standard stuff, just that now, because gain coefficient is slightly larger than 0, right? What you get is basically a splitting that is becoming smaller. Instead of having the splitting kappa, you now have a splitting of a square root of kappa square minus gamma square. More interestingly, and possibly more importantly, if your gamma is very high, then it becomes more than kappa. And as a result of that, whatever the argument that you have under this square root becomes negative. That means that it becomes, you get an imaginary number. So you get two modes. Now, rather than they be splitting in the real frequency domain, the way that we have it here, they split in the imaginary domain. And we know that imaginary part of the frequency, complex eigenfrequency, basically gives you the amount of gain loss or the quality factor of these resonances. So basically you get two resonances one of them with a very high quality factor or very high, resonant properties, and then the other one with a lot of loss, and that basically you basically get this enhanced gain contrast that you see in the system. So the system, all you need to do here is to keep these things below the threshold and allow this system to actually operate above the threshold, and that's how you get a single mode laser. So over the years, back in 2014, we actually looked at this experimentally as well. This is what you see. We had a single ring resonator, and this is the spectrum that we got from this. This is, of course, in the logarithmic scale. That's why the resonances don't look very sharp and clean. Now, if you look at the coupled system, where both of them are actually subject to gain, you see this is splitting, as we talked about it. And once you actually apply, so there is this in this system, in this case, in the lower, system, what we had was another ring here. What we have is another ring here, but it's not pumped. As a result of that, you don't see any light in it. Here, because we are operating the system in such a way that that mode with the highest gain will be in the PT broken phase, what you observe is that the system becomes single moded very nicely, and it is as I will show in a minute, you will see that it has other benefits as well. So to compare these three systems with each other, first of all, what I want to compare is that peak pump power per ring versus the normalized intensity. This is the intensity I get from the whole system. So as you can see, when I basically normalize everything per ring, all three systems show pretty much the same slope efficiency. That means that not all of them, basically, even though we are having loss in this system because we are basically not pumping one of these resonators here, that doesn't affect the system, because remember, the mode is reshaping and goes to the resonator with gain, and that's why you get all the energy to be here. So basically this mode doesn't even see the loss of this one, even though they are coupled. And that's the beauty of, it's a little bit counterintuitive the way that it works, but that's how it works. So this is an indication to this behavior, that all these three systems are pretty much the same slope efficiency. Now, more importantly, if we compare the power that we get in this one peak with that you get from this peak over here, you can see that this one has 4 times more power per this frequency, per this peak. And remember, that's basically what it means is that as if the system gets all the energy that is, previously distributed in all these 4 modes, and send all of them into this mode of the, the chosen or mode of the system, of the coupled system. And that's what you see here. So if we compare, and this is most of the time, that's the parameter that we actually care. We want from a laser to generate all the power, to have a lot of spectral purity, all the power in one single mode. We don't want to get many modes, and the power is basically distributed in many frequencies. And that's basically, as you can see, it does the job in that sense. So as I said, over the years, we looked at many different systems, many different arrangements that were supporting exceptional points for lasing application. And for example, you can here see what was called the dark state laser. This is a laser that composed of two rings with different radius, and they were coupled not directly to each other, but through an additional waveguide in between them. And we can show, and this was a proposal by someone else, but we actually just did the experiment for it and demonstrated this type of lasers and its behavior. It's wildly tunable, and it's a very nice, single mode laser. Use this concept to show, even if you have a broad area laser, you can actually use this thresholding that is given to you by the various, modes and their coupling versus the amount of gain loss as a way to actually make these multi-mode broad area lasers to become also single moded. Now this one is where you have, we had 2 arrays of waveguides, and one array, we designed one array in such a, one array was a standard, equidistance waveguide array of lasers. The other array, which we called it the supersymmetric partner, was designed in such a way that it matched all the transverse modes but the fundamental mode of the main array. And through this supersymmetric transformation, you can actually do this sort of designs. And what we observed was actually, if we now apply to one of the arrays, the main array, we apply gain, and to the supersymmetric partner loss, we can actually couple all the modes that they were matched to the other array. We can couple them, and because they're coupled to the lossy waveguide, they would experience a lot of loss. But the fundamental mode of the main array didn't have any counterpart in the this auxiliary array of supersymmetric partner, was able to actually just go through the system, enjoy all the gain, and as a result of that, we were able to show a single transverse mode behavior from these arrays just by this very simple trick. And of course, we also use this, and others as well, use this trick of using the exceptional point that you get in a single ring in order to enforce unidirectional behavior in the ring. So we know that a ring resonator supports Whisper gallery modes, and Whisper gallery modes are basically mode of orbital angular momentum of the Whisper gallery order. So let's say if we have Whisper gallery mode of order 100, basically that is representing an orbital angular momentum of 100. Now, what happens in this system as a lasers, if you just have a ring, because no ring actually supports just a unidirectional mode, it supports two counter-propagating Whisper gallery modes, the net orbital angular momentum that you get from this system becomes equal to 0. Now, if you can actually break this, the symmetry between these two modes, the two counter-propagating modes, meaning that the CW and CCW modes, you can actually now get a net orbital angular momentum out of this system. And if you have, there are tricks that actually down convert this very high orbital angular momentum to much lower numbers. And this is what we did. This is the result that you can see here. So the next topic that I would like to talk about in these applications of this non-Hermitian systems are what is known as the enhanced sensitivity. So we know that optical resonators are used for sensors, and the principle behind these sensors is very simple, in the sense that they are resonators, they have resonances, and by bringing a target next to this resonator, the environment of this resonator is changing, and as a result of that, the resonant frequency shifts. And this is very well known, that the shift in the resonant frequency is proportional to the shift of basically to the linearly proportional to the change in the index that you are imposing. Of course, there are now many ways to do the sensors. All of them work based on this very simple principle, fundamentally. The only difference between them is how closely you can bring this target to the resonator, what type of material you use, what is the quality factor of this resonator, and things of that sort. So the sensitivity, as I said, is nothing to do with the quality factor. It's basically only it's very you can actually, in optics, we usually teach it to the student that delta lambda is equal to C delta C over N. Delta lambda over lambda is equal to C over delta N over N effectively. So what you see here is that the change in the frequency is proportional directly to the delta N. And so this is known. And the reason for this is also comes from a very fundamental level, because as I said, we make these resonators to be as close as possible to a Hermitian system, meaning that we want to make the losses as small as possible. So they are very good they're very good representatives of Hermitian arrangements. So in Hermitian arrangements, quantum mechanics, the Hermitian theory of quantum mechanics tells us that if you perturb a Hermitian Hamiltonian, the response that the system, the eigenspectra, will change according to this equation. So what does this equation tells us is that the perturbation will be at best, affect the system in this level. So the system will be at best perfect, affected by the first order by epsilon itself, right? Of course, epsilon is a small number. Epsilon squared is even a smaller number. So these are all we can actually, ignore them because they become so much smaller. So the best that this system is changing is proportional to epsilon. Now, if you have a non-Hermitian system that is biased at an exceptional point of order n, and what we mean by an exceptional point of order n is an exceptional point in which n eigenvalues become equal to each other. So we have, for example, n or n plus n something larger than n degrees of freedom. And in these systems, n eigenvalues coalesce on top of each other. N eigenvectors become also collinear, and this is what you get. So if you are biasing a non-Hermitian system at this point, you can show that now if you perturb it, it follows this equation. What does this equation mean? It means that the system actually follows to the best response that it has is basically proportional to the nth root of the epsilon. Again, I would like to remind you that epsilon is a small number. So it's, for example, the second root is going to be larger than epsilon itself. And the cubic root is going to be even larger than that, and so on and so forth. So as you go to higher and higher the exceptional point, you can fundamentally, and this is what's important here, is because this is now nothing to do with you are actually changing any arrangement. It's just that you design a system that is biased at an exceptional point of order n, and you immediately get an enhancement of the sensitivity that is on the order of n, the square root of nth root of epsilon. So again, to give you an example is how we are generating this exceptional points of different orders. Here is, for example, you have seen that at the beginning of my talk, that if we have two resonators, one subject to gain and the other one subject to loss, we can generate a second order exceptional point, or just the exceptional point, we called it back then. And if you have three resonators and you pump them following this arrangement, meaning that one of them is lossy, the other one subject to gain, and the middle one remains neutral, you can get a third order exceptional point. Of course, you have to also design the kappas. If you want a fourth order exceptional point, you can see that such an arrangement will do the job by having four resonators, one bit loss, a lower level of loss, less gain, and then higher gain. And now if you look at the behavior of this system, this is what numerics shows us, that if you basically apply very small perturbation, you can see that this is what you expect from a single cavity. This is what you expect from a second order system that is high, biased at the second order exceptional point. And this is what from the third order exceptional point, and so on and so forth. So you can immediately see that this resonance shift increases as you go to higher and higher order exceptional points. And so back in 2017, we did some experiments to show this behavior. So what we did, I put here the 3-ring resonator system, but we made 2-ring and 3-ring systems. And for a 2-ring system, what we observed, as you could see here, we see a wavelength splitting that follows this curve. And if we draw this in the log scale, we can see that the slope of this line is 1/2, indicating that we are having a square root behavior. And we also, in this system, we saw almost 13 times enhancement of sensitivity. Now, we also did an experiment to show that this what happens for the third order exceptional points. Somebody asked, with 4 resonators, does n is equal to 4? Yes, that's basically we can design the 4 resonator systems to have no exceptional point, 1 exceptional point of order 2, exceptional point of order 3, or exceptional point of order 4. Okay. All right. So now in this system, as I didn't say, but let me just clarify that the way that we are applying the perturbation is through thermo-optic coefficient. So basically, we put these microheaters below resonators, and we are basically applying current to them. And as a result of that, we are applying the perturbation. They are pumped based on whatever we want to generate. A third order exceptional point or second order exceptional point, they would have different pump. Now, this is the result of the second order exceptional point, and this is what we got from the third order exceptional point. I usually like to show this one because it's an interesting way of recognizing an unusual behavior around the exceptional point. So you can see that we had three resonators. One of them we pump it, the other one we don't pump it, and one of them is basically we are pumping half-half or something around that. Interestingly, at the exceptional point, the eigenmode of the system will follow this equation, which is basically, as you can see, the intensity is going to be 1, 2, and 1. And look at the intensity that you see in each of the rings. Clearly, the middle one, the neutral one, has higher intensity than both of these elements. And this is another indication that we are actually measuring, biasing the system properly at the exceptional point. So this is when the system is biased at the exceptional point. We apply the, as I said, with thermo-optic coefficient and using the heaters, we are basically changing the index in different resonators. And as you can see, as you are applying the perturbation, the system immediately shows three resonances. And then as you increase this perturbation, these three resonances starts to shift away more and more away from each other. And if we now look at the wavelength splitting that we see as a function of the applied current or the perturbation, we see this third order, this behavior, which if we look at in the log scale, we can see that the slope is 1/3. Again, an indication that we indeed measuring the system. We are seeing this cube root behavior. Also, you can look at here as what we get for the enhanced sensitivity. At some point, it reaches 23 or something like that. So with that, the next question that we asked ourselves was that how we can actually use this, enhanced sensitivity for making, new devices. Of course, whenever we are dealing with sensing applications, there are two aspects that are important. One of them is sensitivity. The other one is what is known as detection limit. So we want very nice and narrow resonances because that allows us to detect better. At the same time, we want high sensitivity so that even if we apply a little bit of a change, it would move a lot and the resonances shift a lot and we can observe them.
Excuse me.
A second, I see a question. Yeah.
Yes. How do you measure the frequency splitting? Do you make a fit of the frequency spectrum?
On that one, yes. Yes, on that one, that's what we do. Okay. So this here, we just get the spectrum and basically we measure it. We identify the peaks and measure the separation.
Another question is,
just go ahead.
Excuse me. With 4 resonators, that means n is equal to 4?
Yes, that was asked before. I answered.
Oh, okay.
So with 4 resonators, we can in principle get an exceptional point of order 4.
Yes.
But of course, if it's non-Hermitian, if it's Hermitian, there is no exceptional point. We can even make gain and loss contrast between 2 elements and get just an exceptional point of order 2. So you have options, right? That's what it is. Okay.
Thank you.
So back again in 2017, we looked and say what can we do with this enhanced sensitivity. So to address that question, we basically said a lot of people are doing, using, they have this very, very nice and very high Q resonators that they can measure, even single molecules. So where is it that we actually want a lot of sensitivity and still there is not enough, we already have gain, because remember, with the non-Hermitian systems, you're going through the pain of introducing gain in the system. So there must be an application that justify all of that. And that's what we basically looked for. And one area that we identified as a possible way where non-Hermitian sensitivity enhancement can actually help, and that's for ring laser gyroscopes. So ring laser gyroscopes are interesting devices. They work based on what is known as Sagnac effect. And so what basically Sagnac effect says is that if you put a resonator in a framing, in a rotating frame, based on the direction of the rotation and the velocity, you get separation between the light that travels in this resonator in the clockwise versus the counterclockwise direction. And if you measure the distance, of course, as soon as you introduce, this is the Sagnac effect. Now, if you introduce gain in this cavity, whatever, so okay, so if you have a resonator and you are basically put it in a frame of, if it's passive, the light travels in one direction, acquires a phase that is different than, you know, the one that rotates in the opposite direction. Now, this is just a phase. Of course, you can identify this phase by, you know, interferometric techniques where you can measure the phase. But at the same time, if you introduce gain inside this cavity, you can bring this phase shift immediately to the spectral domain and see it in the spectrum of the lasing device that you have. So this is basically the principle behind the operation of ring laser gyroscope. So you get this phase shift that you get because of the Sagnac effect, bring it to the spectral domain. So the question was, can we use the sensitivity enhancement non-Hermitian system to develop more sensitive RLGs? And here is a schematic that we had in mind. So we said, let's become very ambitious and think about a ring laser gyroscope that is only 10 micron in radius. It's a very small ring laser gyroscope. So if now you put this ring laser gyroscope in a rotating frame where the gyration speed is 1 degree per hour, based on this formula that you have for the separation between the frequencies due to the this gyration speed, you can see that the gyration speed is, first of all, is always proportional to the size of this resonator. And so it becomes smaller when you go with the smaller ring. And for this particular example, with these numbers that we put, you get 1.2 millihertz separation between the two frequencies. Almost impossible to be detected using, you know, for example, if you have a semiconductor gain system. Now, if you have a PT-symmetric system, we know that the splitting between the frequencies follows the square root of the perturbation. Now, the perturbation here would be whatever you had here, and we get this square root over here. Now, in this system, I have two resonators that are, each of them is 10 micron in radius, and they are coupled to each other because of this interspacing between them that is in the order of 100 nanometer, which you get almost 1 terahertz of splitting. Now, in this system, if we do exactly the same thing of putting in a rotating frame with a 1 degree per hour gyration speed, you will get the separation between the two frequencies will be on the order of 50 kilohertz. Now, this is something that even if you have a semiconductor lasing system, you might be able to observe this amount of separation. So that was the justification that we had back then to make these systems. Interestingly, we know that ring laser gyroscopes are in fact size-dependent system. And one of the problems is that their sensitivity becomes smaller and smaller with the size. Now, with the PT-symmetric ring laser gyroscopes that I just showed you, we can show that the maximum frequency splitting is no longer proportional to the size at all. So it becomes a constant that basically depends on all sorts of parameters of the system, like the refractive index and the group index of the waveguides and that the ring is made of, and the omega 0, which is the frequency, and so on and so forth. So you can see that we can in fact show that at the best, this system becomes independent of the independent of the size. There's a question that says, why are the peaks different heights? James, can you tell me where was it? So that, in just the previous slide. Okay, so because when you do the detuning, you actually push one of the system to, to go to the more lossy system. Remember when we had at the very beginning the two eigenvalues that were one of them seeing more gain and the other one was seeing less gain. So it is the same principle. Even though you are not really moving along that line, you're actually moving in a two-dimensional or three-dimensional space, which I will show you in a few slides down the road. but you are basically the 2 points, the points that you are going to end up at are going to be seeing different amount of gain. That's why they have different heights. Okay, did I answer the question? Yeah. Okay. I can explain more hopefully, like we have time. Okay. So back, we were very desperate to actually demonstrate this experimentally. So we went and bought this standard educational helium-neon ring laser gyroscope and modified it in such a way that it would basically emulate the effect of artificially, basically, we generated this exceptional point. Again, helium-neon ring laser gyroscopes are actually the ones that Honeywell makes, and they are the most sensitive ones at the moment. But this was, of course, an educational one. It's pretty big, you know, everything is free space and so on and so forth. So basically how it works, as I said, you have a resonator. If it's at the, if it's static, if it doesn't rotate, what you expect that you have the two counterclockwise and clockwise modes will see exactly the same frequency because they pass through the same, you know, the trajectory is exactly the same. So, and that's what you see. Now, when you are putting it in a rotating frame, what you observe is that there is a splitting between these two frequencies. Now, if you are making this exceptional point, and the way that we artificially generated the exceptional point in this cavity is by playing with the polarization. So what we did, first of all, the helium neon tube had two Brewster windows, so we have some level of polarization selectivity in the system. We added a half-wave plate and a Faraday rotator. So the way that it goes, the light that, for example, travels in the CW direction, it would see, because of the Faraday rotator and the direction of the half-wave plate and the Brewster windows, it sees, for example, overall less amount of loss than the one that goes through the CCW direction. And because these two modes, because of this echelon, these two modes are also become coupled to each other. So effectively, we expected, if none of that existed, we expected to have one resonance in this system for the clockwise and the counterclockwise that would coincide on top of each other. Now, because of this differential loss, we get separation between them. Because of the, again, because of the coupling, they come back, or you can think about it, because of the coupling, they get separated from each other. And this gain loss contrast, what it does is basically gets these two resonances that because of coupling, they want to run away from each other, push them back to be on the same point again. And that at that point, because it's like you by force, you're keeping the system to act like there is only one resonance. So this is the exceptional point. And now if you are basically perturbing the system or rotating the system, it becomes far more sensitive. And that's what you are observing here. So there's a splitting that is larger. So experimentally, that's what we observed. This is where you have no, you know, coupling and no gain loss. And this is what you get. It's the standard system characterized by the company and by us. And then, of course, we did, both the company and us did these experiments. So we basically added these extra elements in the cavity. And as you can see, first of all, the slope of this function changes, becomes 1/2, while the standard single cavity has a slope of 1. And you can see that you can, in fact, again, back to this equation, you can see that you can also use delta G or delta kappa as a way, or the kappa as a way to increase the, improve the sensitivity as well. And that's what we did too. And this is where the sensitivity enhancement, again, here we actually measured the bit frequency directly. So we didn't go to, you know, measure each of them separately and calculate. As we did this experiment, we also noticed that the group of Vahala, also from Caltech, did a similar type of experiments, in the sense that there were sensitivity enhancement showing also enhanced Dirac sensitivity in lasers based on Brillouin lasers. There were lots of differences between the two systems. This is what it's known as anti-PT symmetric system. Our system was a PT symmetric system. Nevertheless, both of them were supporting an exceptional point, and they were also observed this little, but they observed the enhanced sensitivity. Later on, they showed that in fact the sensitivity, even though you get enhanced sensitivity, but also you are having an increased amount of quantum noise in the system that basically compensate each other. There were other works that actually show that this is happening because of this particular type of gain that is very similar to a linear system, and this is in fact not true for generic systems like the ones that we are studying. Nowadays we are basically trying to do these ring laser gyroscopes on chip. We actually, with the help from Infinera, we built this PT symmetric gyroscopes, and we are characterizing these systems. We even observe almost 50 times enhancement in sensitivity already. We are also observing that when we get closer to the exceptional point, in fact, the resonant frequency, we have an increased amount of noise in the system, but it's now by no means actually it is in such a way that it compensates fully the enhancement that we see from the sensitivity. Now I see that I have 3 minutes. I don't know how much more time I have to. Do you want me to stop? How does it work?
Please move forward. We don't have a hard limit.
Okay, very good. All right. So more recently, I mean, we do a lot of work on non-Hermitian systems. Very recently, we looked at it as another angle. Can we use these PT symmetric couplers instead of standard couplers that are used in optical neural networks? As you may know, there has been a lot of interest in recent years in implementing optical neural networks on chip, and performing some level of either as an accelerators or just for training purposes. So most of these networks work based on very nice theoretical foundation that we can in fact implement any type of a matrix as use what is known as SVD, or singular value decomposition. We can decompose the matrix into 3 matrices. 2 of them are what is known as unitary matrices, or they are basically Hermitian matrices, and the middle one that is not a unitary matrix, and it's a diagonal non-unitary matrix in general. So so the way to, and in optics, we have a very nice way of implementing unitary matrices, because we can in fact use what is known as Mach-Zehnder, Mach-Zehnder arrangements, or the couplers in order to implement unitary matrices. So we get, so in a generic kind of, and this is not the generic, this is the PT symmetric version, but in a generic case of optical neural networks, what we have is, as I said, a network of resonators, a network of couplers. These are all, Hermitian couplers. We add with what is known as Mach-Zehnder couplers, most of them, or interferometers, and with phases. And we have also the same array here. And as I said, in between, we can implement that diagonal matrix that I talked about. So what happens is that in optics, even though this schematic is really good on paper, in optics, implementing these phase shifters is becoming, it's very difficult. Most of the time, because they require larger space, they require, it's basically, the phase shifters are mostly implemented through heaters. And heaters are basically big. Thermo-optic coefficient is a pretty small value, even for silicon. And so as a result of that, you need to apply, you have a large length in order to apply, to have enough, few hundreds, for example, or of micrometer length in order to have 2 pi phase shift. And so the idea that we had was that instead of implementing this system, instead of having these phase shifters, how about if we replace the Mach-Zehnder interferometers with what is known as a PT coupler? And these are the couplers that one arm basically sees gain and the other arm sees loss. And these are PT couplers that are in the PT unbroken phase, where the gain loss contrast is actually very, very small. And we even showed that if you do this, you can get pretty much the same, behavior and response, especially when you do training. You can get the same accuracy level as you get from this Mach-Zehnder-based system. You can, of course, these are very fast systems. In fact, we can show that in terms of power consumption, these systems are much better than what you get from Mach-Zehnders and phase shifters. So there's maybe a little bit of a game to play there. Of course, this is a theory paper. We still need to show some of the experiments along these lines. So I know that I previously promised that I'm going to talk about this 2D when we talked about this detuning and how it changes the system. Remember, we looked at the parameter space and I showed you a line and a 2D curve, and I show exceptional point is in the middle, and this is where we get the gain versus coupling coefficient changes. We see a full spectrum of very, very different behaviors below and above exceptional points. Now, we can even enrich this picture a bit more, even in that very, very simple system, by adding also detuning to the system. Let's say now, not only your resonators are, remember I started with saying that they are identical. How about if they're not identical? They're slightly, their index, the real part of index is slightly different. And as a result of that, they have a little bit of detuning between them. They are still coupled to each other. They are still subject to the same amount of gain and loss. And immediately when you do that and you start to look at what happens to these Riemann surfaces that are representing this system, you see that this is becoming really complex and very, very rich system, in the sense that the geometry of this Riemann surface is no longer that simple one that you expect from the standard Hermitian system. So in a Hermitian system, you expect to see two Riemann surfaces, one associated to eigenvalue 1, where your lambda 1 is basically residing, the other one to eigenvector 2. And as I said, if you are at the exceptional, at the degeneracy point of Hermitian systems, you're basically at this point over here, where the two eigenvalues become equal to each other. Now, as I said, non-Hermitian system give you this page, this type of sheets that are so twisted and so different in many, many ways. So it's basically immediately introduces new, new topics to this area. So one interesting thing that comes up is what happens to the adiabatic theorem. So we know in the adiabatic theorem that if a system is adiabatically if you start to adiabatically change a system and you happen to be in this upper sheet, you expect to stay in that upper sheet. And if you are basically, your eigenvector stays the same. At the very best, your system may actually acquire an extra phase, which is known as Berry phase. Now, the same is true if your system is in this lower, is operating in this lower eigenvalue. You expect that the system would stay there, as you basically you adiabatically change the parameters of the system, and you come back to where you started. So you have an encirclement in this parametric space in a Hermitian system. You will see that the eigenstate remains where it was, but the eigenvalue can at most acquire some phase. Now, in non-Hermitian systems, that's not the case. You can actually start in one of these places, and you start to adiabatically change the system and come back to where you started, and all of a sudden you are ending up in the upper sheet or in another sheet. And as a result of that, you're basically not only seeing that the eigenvalue is changing, but also the eigenvector is changing. And that's I think I got ahead of myself. So this is the adiabatic theorem. Again, if you slowly change the parameters, you stay in the standard adiabatic theorem of quantum mechanics. You're expected to stay in the same Riemann sheet, and the eigenstate remains the same. And this is and you can only at best acquire some extra phase. And this is not the case in non-Hermitian systems. So in non-Hermitian systems, there are two different regimes that becomes important. One of them, when you are actually doing this encircling of the exceptional point or the degeneracy point in a quasi-static way. That means that you basically assign the system at this point, you do a measurement, you put the system over here, you do another measurement, you do the system over here. And even back in 2001, there was experiments that were showing that if you do this very unintuitively, you can actually switch the eigenstates. So if you start from here, you can end up in the other eigenstates and so on and so forth. If you start from here, you can end up here. Now, if you do this dynamically, there would be another, complexity introduced in the system, in the sense that now it becomes important whether you are actually encircling the exceptional point in the clockwise direction or counterclockwise direction. And you could see that, for example, if you go in the clockwise direction, you always get one you always end up at one eigenvector. If you go in the counterclockwise direction, you always end up in another eigenvector. And that's what has been demonstrated over the years, back in 2016 it started, and now has been even shown in silicon systems. So what we did, we basically designed this type of lasers where we have two coupled waveguides. One of them is subject to gain and the other one is subject to loss. And we are introducing the coupling between them. We are basically by designing the shape, we make the coupling to follow this type of equation. And we showed that with the detuning, by adding this extra construct next to them, we are also introducing a detuning, and we are just shaping it in such a way that it would be in this. So one of them is like a cosine function, the other one like a sine function. And you can see that if now we look at the parameter space where we have delta detuning and kappa the coupling, we can if this is our exceptional point, by basically going from one, instead of doing it in time, dynamically in time, we are basically going dynamically in a space. And remember, in optics, especially when we have propagation, time and space are basically very, very much the same thing. So you now hear that basically you can encircle the exceptional point as you're propagating in this thing. So, and if you do it slowly enough, you can see some of this behavior. That's what we did. So this is, you eventually, you expect that in one direction, you always get one mode, and in the other direction, you get always the other mode. We can even show that in the presence of nonlinearities and the lasers, which has the back and forth of the modes, we still see the same behavior. To make the lasers, we actually we put these gratings on top of it, just because these are very, very long lasers, and we get so many longitudinal modes, it becomes very difficult to compare the systems. So after doing that, these are the results. So you can see that in one direction, when we look from the facet of the device, we can actually get the, for example, in this case, out of phase mode, when you have a you have almost a null at the center. And from the other direction, when you look at the the far field, you see the in-phase mode, where you have a maximum of the field at the center. And these are the light curves and the spectrum, which again, you can see that they are very similar. So I think realistically, I should stop at this point, even though I have some interesting stuff to say about topological photonics as well, hopefully in some other occasions.
Thank you very much for the very interesting, nice talk. And
just
yes, we very much enjoyed it. I wish we have enough time to listen to the other topics, maybe another time. So let's Bill asked a question. He's raising the hand. Maybe let's see if I can allow him to talk. Let's see. I'm working on it. Sorry. Bill, would you be able to type in your question, or would you like to speak? I'm working on.
So if you don't mind, there are a couple of questions. Let me just see if I can
Okay.
answer them,
Okay. Yes.
while you
Yes.
figure out how to do
Right.
that. Most studied systems have EP below lasing threshold. Have you observed EP above the lasing threshold, including non-linearities? Yes, indeed. We looked at it. It's actually, I didn't put it, one of the papers I put there, I think maybe 2016, 15 or 16. We looked at what happens with in the presence of nonlinearities. In fact, this picture that I gave you, even though it's good enough for a 1 hour talk, but the physics behind it, it's much more complicated. You can actually design the EP to happen below the lasing threshold, above the lasing threshold, and the system behaves differently. You can get them to get to each other in one mode and then become separated. So yes, Muhammad, the short answer is yes, we did study them, and there is a lot more than this simple picture that I gave you. There is, I think it's a PRA paper with Absar al-Hassan as the first author. If you want, I can send it to you. So the second question is, when do you think that these RLGs will surpass free space ones? Okay, so the current free space ones are really, really good. So when I did, I think it's in the order of 10 to the power of -4 degree per hour. And it is, what we have right now is not even, of course, they're much, much larger. But what we have right now is pretty much, it's 50 times, I think, pretty much 50 times, I think, larger than I have to check it, but I think we talked with the student, either 20 or 50 times larger than the Earth rotation rate. So an Earth rotation rate is not as great, right? So I would say it requires a lot of work. But now there is a lot of improvement in lasers. The laser that we are using right now is linewidth is around few hundreds of kilohertz. So, but now even semiconductor lasers, there are some designs that can go sub-kilohertz. So with that, I can only imagine that things can become like 1,000 times better. So, and what other sensors do you see as hopeful? That's as far as my imagination took me for allergies. I see that other people, there are some work, maybe not at optical frequencies, but maybe at terahertz frequencies where they were used for as biosensors. As I said, I mean, as soon as you're putting it, and then there is no gain. So maybe they are useful there as well in that frequency domain. In optics, actually, we have very good sensors with very, very high quality factors. It's really hard to match them. And because they do the job and they are already passive, so it's hard to compete with them. The only reason that I went with gyroscope was because it already had gain. I mean, so it's already, that's somewhere that we already used the gain. I saw a couple of my colleagues, friends that used this type of gyroscope for accelerometers, not gyroscope, sensors for accelerometers. So maybe there is enough justification to use them, even as passive ones. I did not explore them that much, so I cannot answer that question further. Yeah, I can put the paper in the chat if you give me a minute. Okay.
Thank you. Thank you. Bill?
Can you hear me now?
Yes, yes.
Okay, I have a question and a comment, both on different subjects. The first question is, I found the talk extremely interesting, but it made me think a little bit. In quantum mechanics, general relativity, even mechanics, people have been reformulating that in Clifford algebras. And the advantage of that is, instead of just having, real numbers and imaginary numbers, you have in the Clifford algebra, you build up products of vectors, bivectors, trivectors, quad vectors. And what you find when you express the physics in them, that all these things that square to -1, just like the imaginary does, you find that different physical aspects are attached to different of these multivectors, and it gives you a much deeper insight into what is actually going on, because things you thought ended up before simply because you were squaring an imaginary number, you find are now coming from squaring different other objects that represent different physical properties. So I'm wondering if you have ever thought of expanding this work by expressing it in terms of a type of Clifford algebra, so you could maybe get more insight into the different types of exceptional points that now might all look the same.
The answer is I did not, but it's a very interesting point that you brought up, and I will look into it.
Okay, then my comment is, and I'm going to refer back to quite a while back. I'm retired, but back in the 70s, I spent 8 years working on ring laser gyros. And these are the same gyros now that are found in inertial measurement units in all the Boeing airliners and the Airbus airliners. And the two frequency ring laser gyros, whether they were a square meter in area or inside a 1-inch glass cube, basically, if they were two frequencies, they had line widths of about kilohertz. So a kilohertz subtracted from an optical frequency of 10 to the 15th gave you about a sensitivity of 10 to the 12th. The 4-frequency ring laser gyros that you made by twisting the planar cavity out of plane gave you an extra factor of 10 to the 6th. They had line widths of millihertz. So you added 10 to the 3 to 10 to the 15th, and you had 10 to the 18th sensitivity. So even back in the late 70s, there was more than enough sensitivity than you could ever use on a ring laser gyro. A plane taking off from New York could get within 6 inches of the centerline at Orly Airport in Paris. But all that sensitivity, and this is my point, was sort of useless, because if the temperature of the ring laser gyro changed a little bit, or the current changed a little bit, or the environment changed a little bit, the whole thing went out of calibration. It was so bad that the military, and again, since I'm referring to 40 years ago, I think I can say this, the military never wanted to use them on a rocket, because if the temperature changed a little bit, you had to let it settle for a week in order to stabilize again. So the only point I want to make is, from a practical sense, I believe ring laser gyros have always had more than enough sensitivity. It's just that it was impossible to really stabilize the environment to get one to give you all that sensitivity.
So that is true if you go more than one frequency, right? Or two frequencies, so the splitting happens more. You can get even more. But remember what we had, for example, the one that I showed when we modified the RLG from the Heaney RLG, it's actually, we are not introducing any more resonances. They are exactly the same, we still have two resonances. They are exactly similar to what you get from a very, very simple helium neon ring laser gyroscope. Just that let me make sure that I make the point clear. So you saw that what happens in a standard Hermitian system, you basically always generate this sensitivity or this splitting, because you bring the system to that, you're actually using the system right at that diabolic point, or where the two eigenvalues are exactly equal to each other, and then you basically perturb it and the two eigenvalues go to different direction. That's why you get the splitting, right? Now, if you have the non-Hermitian systems, not only you brought the two eigenvalues to the same point, but by using extra force, which is through gain and loss, you also brought the eigenvectors to the same place. And as a result of that, you change the dimensionality of the system. You see, the Hermitian system, no matter what you do, it always has two dimensions. But the non-Hermitian system, at the exceptional point, has only one dimension. And that's why this system behaves much more drastically to the external perturbation that you apply. It basically it somehow, it shows a much more drastic change or splitting due to this perturbation. So it is very different than you play with several modes, and then of course that can also that can become a problem. This is the same thing, the very, very same thing as you get from a very, very simple just one resonant frequency in one gyros, in one resonator, a degenerate frequency, and then you start to get it splitting. So that's the only point. I mean, of course, you can always find other ways. Even plasmonics most likely has much higher sensitivities than these systems. So I see a couple of more questions. How accurately does gain have to equal loss to stay near an exceptional point? Okay, so I usually put this picture. It's this effect is basically, it's the gain, what is important is delta G, which is gain loss contrast. As I said, it can be gain contrast. It can be gain contrast. It's just a differential gain, or it can be differential loss. You get exactly the same behavior. So you get the exceptional point. So the exceptional point is nothing to do with the absolute value or net value of gain. It only basically happens because of the gain difference. And as a result of that, you don't need to do anything equal. The theory of the PT symmetry is, of course, PT symmetry, which basically is symmetric gain and loss. But practically, this exceptional point happens even without, matching gain and loss exactly to each other. As I said, what matters is the difference. Where it happens doesn't matter. And then there is another question that says, can we have a copy of the slides on our recording? Of course, I already talked to Keisuke, and I'm gonna send the slides to him.
Yes, so the recording and the slides will be available online in a few days. Please check our website again. Okay, thank you very much for your very interesting talk.
Thank you very much for having me, and very good questions.
Yes, thank you very much. And let's clap our hands.
Thank you. Have a great day.
Thank you very much. Have a good day.
Thank you.
Thank you, everybody.